but it's been through about 3 major revisions, complete rewrites. So, but I keep using the same name. So you've seen versions of this before. It's probably different. So this language is, on the surface, it looks much like Haskell. It's a dialect of Haskell. So I'm just showing some example code which does Conway's game of life. So you can define data types. You can write functions. So that's defining cells of game of life. Then I have, this is just interest of, define arrays, and then this pattern matching and data constructors, that sort of thing. So I showed that this really does work, and then, so I can build the file, and then run it. So it plays Conway's game of life. So it's got a compiler which compiles down to LLVM using a typed intermediate language and a working garbage collector runtime system. So it's a real language. It's got some rough edges which I'm still working on, but it's usable. Okay, so the claim to fame of DDC and the main focus of my PhD work was to have a better way to manage effects. We know in Haskell, everyone's done Haskell. Yes? Yes, yes. We have this IO monad thing. So I'm going to talk about that. I'm going to go to some slides. I've shown some code. I'll do slides, then go back to code. So that was the one one. So with this talk, I'm going to start with this simple data type. I've got 2 things. I've got red and blue, just an example. And we can write wonderful pure functions with these data types. I'm going to look at what a boolean is, and if it's true, go to red. If it's false, go to blue. That's no worries. Things get a bit more sticky in Haskell if you start to use side effects. So suppose I have, instead of a boolean, which is a pure value, I have a heap allocated reference which contains a boolean value. And then before I do this match, I need to read the reference. And then the readRef function might have a type like this. I get ref A to an A thing. Now, this is the sort of code that you would write in a so-called impure language like OCaml or Scala, something like that. So we're doing a side effect or computational effect in the middle of a block of code, but the type signature doesn't reveal the fact that this effect is taking place. Okay, this will be familiar with people which have done Haskell. Now, the fact that the type signature doesn't reveal that the side effect is taking place means it's very hard to do code motion style program optimizations like stream fusion, array fusion, worker, wrapper, all the inlining and stuff which GHC does. So it's convenient to be able to use these side effecting functions, but it causes problems in other areas. Now in Haskell, we have this wonderful thing called the IO monad. So what IO allows us to do, really, is to have a richer type. So I'm going to give readRef this type ref A to IOA, and the fact that this is an IOA rather than just a regular A reveals that this is performing some computational effect. And you want in the type of the overall function to also show that this function is doing an IO action before you get back a color. But then if we do this, we can't write this code anymore. ReadRef x, assuming x is a boolean, has type IO bool, but I can't do a case match against a bool. Okay? So this program has the type that I want, but I can't write it like I want it to. So it's less convenient than the impure one that we saw before. So in Haskell, you have to use do notation. So I'm going to use do notation to write a monadic bind, which performs the computation, binds the result to x prime, and then do the case match on x prime. So we have the type that we want, but we've had to refactor the code, which has been annoying me for 10 years or so. It's like, why should you have to do this? If Haskell is the best language, why do you have to adjust code just to get the types that you want. So this transformation just from there to there in itself is fairly trivial. Like you could think, oh, you're just a complainer, just write it like that. It's not too bad. But if you write bigger programs with more interesting control flow, this problem becomes a lot more serious. For example, we have these things called pattern alternatives in Haskell, which provide a very very useful notion of control flow. So if you haven't seen pattern alternatives before, the way this works is that we test if n is more than 5. If it is, we match the color against red, and if that matches, we go to this result blue. But if any of these guards fail, if any of these fail, then we go to the next block. And if we have more blocks of alternatives, if any of these guards fail, we go to the next block, and so on. So this is a richer notion of control flow than case expressions, which is a useful feature of Haskell. But then suppose we want to do the same sort of thing as before. We want to use computational effects in the guards of our pattern alternatives. Once again, this sort of thing doesn't work in Haskell. So I want to read my reference in the right of a pattern alternative guard, but I can't do that because red has type color and readrefc has type IO bool, and the types don't match. And then there's no do notation which I can write in this form which makes this work. I have to completely rewrite this function, which, yeah, sad story. So I'll show you a better way. So here's the original pure function that we had. And I'm going to introduce two new keywords, this run keyword and box. These are new keywords and primitives in the language. And I'm going to give readref a new type. So instead of saying ref a to io a, now I have readref has type ref a to s read a. What this S is, you can imagine that means suspended computation, much like when you have an IOA, it's a box which holds a computation that when you run it, it performs an IO action and gives you an A thing. Whereas this thing is a suspended computation that when you run it, it performs a read effect. It reads the heap, reads the reference, and then gives you an A thing. So this is much like IO, except it's indexed by the sort of effect which will happen when you run this computation. Okay? Everyone's cool with that? So S, imagine it means suspended computation or S for stent. Either of those work. So what's going on with this run and box thing? I'm going to start looking at what the types of these sub-expressions are. So in this red marked expression, I have readref x. X has type ref bool, so A here is bool. So the type of this expression is s read bool. So that's the type. I'm also going to start tracking effect information directly in the system. I'm going to say that this expression has type s read bool, but it's also a pure expression. Just applying readref to its first argument doesn't perform any effect. It just returns the suspended computation. So that's a pure expression, but it has that type. Now, the result of this is a suspended computation, and when you want to actually run that suspended computation, you say run, and then it lets the effects out of the box, and then you're going. So I say run readref. So now what's happened? When you run a suspended computation which returns a bool, you get back a value of type bool, but the effect of the whole sub-expression is now this read. Okay, so I'm tracking these two different things, the type as well as the effect of the sub-expression. And now, because this sub-expression has type bool, I can do a case match on it. I can If it's true, go to red, false, go to blue, no problem. Which also means that this overall expression has type color, and it still performs a read effect, because this thing has to perform a read effect. So I have these two bits of information, and I've got color, it has type color, and effect read. I let an effect out of a box. If I want to put the effect back in a box, I use the box keyword. So when I box up this effectful expression, I get back a suspended computation. So this whole thing is a suspended computation which, if I was to run it again, it would perform a read effect and return a color, and the whole thing is pure. So now I have a pure value again, which is a suspended computation. And it's that pure value which is the body of my function. So the type of this overall function, well, it says it takes a reference to a Boolean and returns a suspended computation which wants to perform a read effect and will return a value which is a color. Okay? Does everyone follow that? Good. So run, this magical run here, is safe to perform I/O. If you've used unsafe perform I/O in Haskell, you know how dirty it even feels to say that word. Unsafe perform I/O has type IOA to A. So when you unsafe perform I/O and I/O computation, the reason that is unsafe is because it forgets about the fact that there was a read effect or an I/O effect there. Okay, it just forgets. This new system, when you perform these computations, it remembers what the effect of the computation is, and then you can take an effect for computation and box it back up again and get a type safe result. So run is like safe perform. Now, how many people know what that is? Just okay, half. Okay, so these are typing rules which express a type system for the simply typed lambda calculus. And if you haven't seen these sorts of rules before, then just try and extract the general gist of what I'm just going to say. So at the top here I say gamma here is an environment, and it says that if I want to find the type of a variable x, I can check that there's a binding in the environment for that variable of type tau, and then x has type tau. I have this abstraction rule. When I type check an abstraction, I add the parameter to the type environment, and I check the body of the term, body of the abstraction, and if that's type tau2, then the type of the overall function abstraction is tau1 to tau2. And then for application, if m1 is a function, it takes a parameter of type tau1 and produces a result of type tau2, and the argument has the matching type, then the result of the whole thing is tau2. So this is simply type lambda calculus. Now, when you add the effect system on top of this, the reason that my effect system is the best one is because it's a clean extension of what we already had. Okay? So we have pure, simply typed lambda calculus, and when you add the effect system on top of that, it doesn't mess up anything that we already had. So it's a clean extension. Notice that the blue parts which I've added don't touch any of the stuff that was already there. Okay? So at the top I say that if you have a variable and you use a variable, that's a pure computation. I haven't done anything. When I form a function abstraction, that's also just a value, so it's a pure computation. And importantly, when I perform a function application, what this means is that when I evaluate the functional expression, doing that evaluation might have type effect sigma 1. So this is a variable which ranges over effects. Evaluating the argument might have effect sigma 2, which means evaluating this whole function application has the effect of evaluating this and evaluating that. So it's compositional, and it hasn't messed up any of the existing pure lambda calculus. Now there's two rules which I introduce to handle run and box. So what this one says, that if I want to run, apply run to some term, the term has to be a suspended computation of some effect sigma 1, and it's going to have a result type tau. So that's the type of the value that's returned by this expression. And then to compute that value, it might perform some other effects sigma 2. So what's the effect of this overall expression? Well, it's the effect of working out the suspended computation and plus the effect of actually running it. So I evaluate an expression which returns a value, which is a suspended computation, and to do that, I did effects sigma 2, and then when I actually run the computation, it releases more effects, sigma 1, so the overall effect is sigma 1 plus sigma 2. And then when you box things up, if I have an effectful expression, which when it completes will return a value of type tau, and when it does its computation, it has effects sigma 1, when I box it up, the result is a suspended computation which will have the same effects when I release it, and then it will return the type tau 1, and that's pure.
Can't you box half of the effects?
Pardon?
Can't you box half of the effects? Can't you box only part of the effects, not all the effects? And your result is as pure effect.
That's right, that's right.
But can you box only part of the effects?
No. So if you've looked at algebraic effects, you can, in a sense, box up only part of the effects, but this system, it's not like that. We can talk about that afterwards at the end. So you have to box up all the effects at once.
So what's the meaning of supports in this case?
So we'll get to this. So there's a capability system which will allow you to track in the context the effects that you're allowed to perform at any particular point in the program. And I'll talk about that a bit later. Okay, so if you didn't follow the typing rules part, the takeaway message is that it's a conservative extension or a clean extension of the pure simply typed lambda calculus. We haven't messed anything up that we already have. So if you've looked at effect systems before, I'm not sure how many people have, but there's another way of tracking effect information, which is called a latent effect system. And in those sort of systems, they combine the effect information or the effect typing information with the type of the function arrow. So in a system which uses latent effects, the type of a function might be something like tau 1 to tau 2, so that's the type of the parameter and the type of the result. And you write E above the arrow, which says that when I perform this function application, then it's also going to do some effects, say E. Now this is one of those situations where you're messing up what you had before. Because really, in a pure language, what the function arrow means is just substitution. Okay? When I write a lambda abstraction, I have define a function, and when I apply that function to something, I just substitute into the body. That's what happens in a pure lambda calculus. But when I write an E above the arrow, it means that this arrow doesn't just mean substitution anymore, it means substitution as well as doing something else. So I've mixed the two things up. With the so-called effect index computation types, where this thing is a computation type and I've indexed it by the effects that it had, the arrow still means substitution as before, and I keep the effect information separate. And they're not monads, so I lied in my talk title. I said automatically escaping monads, because it's like when you run. Who's been trapped in a monad? I sure have been. You start writing code in the IO monad, and you say, oh, I have a thing of type IO bool. How do I get out of the IO and just get the bool? Well, you can unsafe perform IO, or you can run it in this system. So the talk was called automatically escaping monads, but these computation types are not monads because to work with them I use run and box. I don't use return and bind. So to be a monad you have to have a type instructor, return and bind, and the 3 monad laws. I don't have return and bind, so they're not monads. They're indexed computation types. Now, going back to the code, I've introduced these two new keywords, and you could say then, inserting run and box everywhere looks even more annoying than what we had before, when we had to refactor the code to use do notation. Like, what have we really achieved? Well, there's a trick. If you have a look at where the runs and boxes are, it turns out that you can automatically insert them. And it's always correct to automatically insert run and box. So just imagine, we wrote that and we didn't have the run. So I've taken the run away. And you can ask, well, what's the type of read ref x? Well, read ref x has type s read a, but then in the context I've used it, you can see that this case expression wants something wants a boolean. So that actually this is a s read bool, but the computation itself just wants a bool, not an s read bool. So based on that contextual information I know, I can just insert a run there to actually run the computation and then get the boolean out. And it's always safe to do that. It's always safe to put the run in that point, because if I didn't, I would get the type error. So you might as well just put it in.
Is this operation like decidable?
Pardon?
Is it decidable or?
We just decided.
Well.
So if you have a look at the other one, so this box, say if I take the box away, and we just write that, well, the type of this whole expression is color, and the effect is to read from the reference. But I said before that we haven't messed up the pure lambda calculus. So in the pure lambda calculus, the body of a function abstraction must be pure. This is not pure. So I can make it pure by boxing it up. And it's always safe to do that. So I can put the box back in. So I can go from there back to there. I automatically insert these. So in the actual language, you write your code just naturally as you would if you're writing a camel or something. And then the type checker automatically inserts run and box as necessary, and you get the types that you wanted at the end of it. Okay. So there's other things like that. You can ask, well, are these the only 2 situations where I have to insert run and box? Those are pretty obvious ones, but it's not the only situations. Some other situations are like this. Suppose you have an add function which just works on natural numbers, takes a nat and produces a nat, and then you apply that add to read refs. So read ref x again might have type s read nat, but if you have type s read nat, but add wants a nat, just a nat by itself, you can always insert run. So there's a few other cases, but they're all easy to spot and easy to handle.
Isn't this case out of parentheses, right?
Pardon?
I would have expected run parentheses read ref y.
Yeah, so maybe that's a bit confusing because run is a keyword. It always
okay.
It's not it's got a lower precedence than function application.
And is it such that at runtime run and box don't have a cost, or do they?
Yes and no. So you could imagine a naive implementation where when you boxed up a computation, it just built a thunk, and when you ran it, it ran the thunk. And you could build a naive implementation which does that. So in my actual compiler, it's a bit smarter than that. So if you have a function, if you've taken a function and compile it down to, say, LLVM, and the result type is a suspended computation, you can always decide whether or not you need to box up you can decide whether or not to build the real thunk at the call site, not at the callee. If that makes sense. I need a better way of explaining that. So we go back to this function. 6 is referable to a suspended computation read color. You can imagine if we were to compile this down to, say, C or LLVM, in the implementation, you could write a C function which takes a parameter, and then what it returns is really a heap allocated object which represents the boxed up computation. Okay? And every time you call this function, it allocates the result and then returns it. And then at the call site of 6, you would have to provide the argument, and then when you get the thunk, you have to run it at the call site. But you could invert this and say that when I compile this code, I take a ref bool and only ever return the color, not a suspended color. And then at the call site, you decide whether or not you need to build a suspension. So there's that optimization. So in most cases, you can avoid building the real suspension on T. Though if you want to have a list full of suspended computations, you have to actually allocate them. That's a good question. Yeah.
So what I meant is that if you have you write these programs like this without this box around this,
Yep.
right? Now my question was, if you have a program that can be made well typed in this core calculus by inserting box and monads, do you always find this insert?
I don't know, that would be interesting to prove.
Okay. So it's not
Interesting question.
so it's not decidable as far as we know.
We don't know whether it's decidable.
We don't know. I'm gonna assume not.
I don't know, that's an interesting question. There are cases, so this, the type checker I wrote is based on bidirectional type inference. In bidirectional type inference, when you're walking down the abstract syntax tree, type checking things, you carry down from above the expected type of things. And then you get to a point and you want to do a bottom-up reconstruction of the type of something, and then you can compare the expected type to the inferred type, and if they don't match, you can insert an implicit coercion, like a run or a box, to make them match. Just bidirectional type inference itself has limitations. It doesn't always infer the types of the things that you might want, because of the order it sees constraints and things like that.
So you just do bidirectional, you don't do like classic in linear, man?
No, it's based on bidirectional type inference.
Okay, so it's less, so like if you need like some non-local information to infer a type, it won't
Yeah,
work.
it doesn't work as well. So,
Okay.
so I've added a bit of non-local stuff to it as a hack, but it could be put on a better footing.
That's interesting, because like usually just with bidirectional type checking is a bit of a pain.
What's that?
It's a pain to use languages that only have bidirectional type checking. I don't know if this is not a pain for some reason.
It's a pain in some areas, but
Okay.
we'll come back to this. So speaking of bidirectional type inference, so if you haven't seen bidirectional type inference, I'll just skip over it a bit, but you separate the type checking judgment into two parts. You have a synthesis form where, for example, given a variable at the top, I can synthesize the type tau. Synthesize meaning that I already have enough local information to tell you what the type of that expression is. So if I have a variable, I can just look up in the context and then give you the type of that, which is synthesized. I use the right arrow for that. Then I have this other mode called checking. If I have a lambda abstraction here, and I haven't got a type on the parameter, but I know from the context that this lambda abstraction should have type tau1 to tau2, then I can just use tau1 as the type of the parameter and then check the body of the abstraction against the result type. So this is a standard in bidirectional type inference. And then for applications, if I have a functional expression applied to some argument, I can synthesize the type of the functional expression and then check that the argument has the same type as the parameter. So the function expects a type of parameter type tau1, and I check that the argument has the same type.
Do you accept lambdas applies to arguments, or do you accept a lambda applied to an argument, or
Sure.
do you? So you can type things explicitly also,
Yes, you can.
because otherwise, okay.
Yeah, you can. This is just the simplest.
Okay, no,
application
sorry,
of
yeah.
bidirectional inference. So you know about bidirectional inference already because GHC will often complain inferred type does not match expected type. So the inferred type is the type it computes just from the expression. The expected type is the type that it has from the type signatures that you have written yourself. So the synthesized type is the inferred type. The expected type is the one that you're checking against. So GHC has some of this bidirectionality anyway. So when you formulate a bidirectional type checker, there's this magic rule which coerces between inferred information and expected information. For example, so this line here says that I have some expression and I want to check that it has type tau2. What I can do is to take the expression and infer some type tau1, and that's okay provided tau1 is a subtype of tau2. An example, I'm checking that M is a fruit. I infer that M is an apple. That's okay because apple is a fruit. Okay. I want to check that M is a vehicle. I infer that M is a train. That's okay because the train is a vehicle. So this is the role that this rule takes. So if you ever need a type checker for dealing with subtyping, the bidirectional type checking is the way to go because it has this rule. But you can also hook other things onto it. So here we go. I want to check that my expression has type tau1, but I infer that the expression is a suspended computation, which is going to do some stuff, and then give me a tau1. That's okay, because I can always run this expression, or I can run the suspended computation to actually perform the computation, and then I have a tau1. Okay? And the overall effect of that, again, is the effect of getting the suspended computation as well as the effect of actually letting it out and running. Okay, so you can hook this coercion onto this standard place in bidirectional type inference. So it's not magic.
So this reads, is there sort of a magic inferred split going on? So it reads like you partition the effect which you have from the environment, which you have available, into the sigma 1 which you need and the sigma 2 which...
No, you don't have to partition it because this is all still syntax directed. So in this relation, algorithmically, I have a context and I have a term and I have the expected type. So I can then use that information to get the inferred type of that, so that I know that this, the type of this is a suspended computation of that effect type and that result value. and I know that the effect of coming up with that value is sigma 2, and then from that information I can build this. So this, and this is an input. I use those inputs to compute that, and then I use that to produce this. So I don't have to do some weird unification where I'm guessing how to split the effects up into these two factors.
Just see that then correctly, that what was confusing me is that in the standard bidirectional type checking, the full type would be given, so the whole right hand side of this double left arrow is sort of, this is the type that's given, check that that the term has this type.
Yep.
But here it's only type 1 that's given, and actually the other side, the effects, is something that is output of the checking mode.
That's right.
Okay.
Yeah, that's right. So yeah, so this is input, 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 and the effects are output, always. Okay. Does this even work? Would be a question you might ask, and I can show you that it does. So here's a example code that exhibits that problem I showed before. So I have happened to use the name 5. So I have a case expression which performs a read ref right there. So read ref has type suspended computation, which will read and then produce the value. I have 5 pat is a pure function which uses pattern alternatives, and I have 5 ref, which is an effectful function which uses a effectful computation in the right of a guard. Okay. So if you want to have a play around with this yourself, you can take a source file like this and then run the type checker on it, and then do type checking, and as well as see what happens when it automatically inserts those run-on box casts and it's being converted to the core language. So we go, you say bin DDC load, and then that file. And here we go. So this is the same program converted to our core language. Core language is a, whoa, nothing there. There we go. Much like GHC core, in that it's a explicitly typed language based on system F. So in this syntax, these brackets mean for all R, and this is the type lambda, value lambda, and you can see that this function 5 now is being desugared, and it's inserted the run cast where it needs to. So, and then the 5 pat was the one which uses pattern alternatives. It's desugared the pattern alternatives into just case expressions. And then here, 5ref is the version which uses the effects in the guards, and it's automatically inserted the run box. Okay.
So, question.
Yeah.
So I'm assuming that things like read are actually built into the language and the compiler understands them. So,
yes.
I was kind of wondering, in Haskell, I/O gives you also ordering, like very explicit ordering of what happens next, and it forces that the compiler will not reorder things that it shouldn't.
Yeah.
And so I'm assuming that the DDC is going to know that, oh, read things, I can actually reorder them and optimize them, but if I have a read and write, then I can't start,
That's correct.
run them.
So I'll show go back to this life example. And then, so there's a few more features. So here we go. So this is the code, which is the main animation loop of that life example, so which draws the frames on the screen. So you can have a look. What's the type of this? Well, animate takes the definition of the world, which is the cells I have in the life game, the current frame and the maximum frame I'm going to, and whether or not I want to insert a slight pause between showing each frame so it looks nicer to watch. And you see what's the type of the result? The type of the result is a suspended computation which will perform a console action, which means writing to the screen. It will also sleep a little bit, maybe potentially, it will potentially perform a read from a thing called a region called R, which I'll talk about in a moment, and it might also allocate objects into that region. So the built-in effects in the system are read, write, and allocate. These are so-called internal effects because read, write, and allocate concerns memory, which the program itself allocates, and is under the control of the language. We have other sorts of effects called world effects, which affect the outside world. For example, printing to the screen or the console as it's sleeping, which has a time-based effect. So in this system, read, write, and allocate are baked in, but you can define your own world effects. Okay. Which I might even have. No, not in this file. But yeah, just a effect. So go back to this. Oh, where was it? Sorry, I'm jumping all over the place.
Does that mean that the compiler is free to say reorder things like writing to memory and then printing something on screen?
That's right. That's right. So if it has a one statement which performs a read effect and another statement which performs printing to the screen, you can reorder those because it knows that they don't interfere.
Right. Yeah.
They don't interfere. Yeah.
Just a quick question. Back where you had that effect, console plus sleep plus
Yep.
read and so on.
Yep.
When you're writing those down, can you have them in any order that you want?
Yeah. So here's another example up here.
Yeah.
So I got a read effect as well as an allocation effect, and this means the same as the.
And did you choose R because sorry? Did you choose plus as your operator because it's commutative?
That's right.
Yeah. Nice
So it's
choice.
commutative.
Can you abstract over effects? Because if you have a higher order function like suspended computation, it has a read effect and something else.
Yeah. So, for example, I need to go to. I'll show you the list library, which has higher order functions which work on lists. Base data list. Yes. Where's one? Yeah. Fold S. So here's a left fold, but the worker function that it works on can be suspended computation which performs some effects. So this fold function works for any worker function which takes a B and an A and performs some action which has some effect E and then returns a result of type B. So it's polymorphic over the effect of the computation.
If I had S of E1 plus E2, would that be simplified to just E? Or so what equation theory do you use to compare effect with free variables?
It will have to end up. So what happens there? It's rejected if it's on the left-hand side.
It's more like row polymorphism, like where you say you have these concrete
No,
things
it's not-
and
it's
this
not.
free. Not saying, I mean, just like the notation wise. If the concrete, you can give a bunch of concrete ones and then just one.
It'll check if two effects are equivalent, but it won't try and work out a factorization to make effect variables unified.
So you consider essentially the plus to be a multiset.
A set former, yeah.
Is set or multiset? Like on the variables which you don't, like on the unknown variables.
Yeah. So what do you mean by multiset? So explain what.
So would you consider E to be equal to the effect E1 plus E2?
Depends on what E turns out to be. So
And if
if
both of them were abstract?
then they're different. So if the
I mean, wouldn't unify E?
well if E is otherwise unconstrained,
Right.
it'll unify E with E1 plus E2. But if you have like a E1, E2 on one hand, and then EA, EB, EC on the other hand, it's not going to try and factorize it to make that work. It'll just say these are different.
Yeah, that's what I mean sort of by the multi-set effect, that if the plus was interpreted just as adding one element into the multi-set,
Yeah.
or multi-set unit, then that is fine, because you can't play with multiplicities.
Yeah, that's right. So in practice, that question doesn't really come up, because when you write these higher order functions, you always just end up supplying a single variable there, because you want your function to work for worker functions which return suspended computations of any type. I mean, there's no reason in a higher order function to say E1 plus E2 there, because you just want it to be generic.
Yeah, I fully agree. I was more trying to see sort of how the mechanics. Is it such that this would also be inferred? So if I wouldn't give any type annotation, would it tell me that fold S has this?
That's right.
It looks the same as the
It's a
fold
fold,
L itself,
Yeah,
so
exactly.
Keeping in mind that it would infer it if you put the runs and the boxes in.
okay.
So
If I left it.
Because at the moment,
Here,
in one of the
here,
boxes, we
I have
have
F-
this context, right? So
yeah, I have FZX, and when I apply F to Z and X, the type is a suspended computation which performs an E effect and gives a B, but then it's expecting Z of type B. So when I type check this, it's going to insert a run at this point. So if you don't have those coercions and you try and infer the type with no annotations, it'll give you the pure version.
Yeah.
But if you had those coercions there, prime box, it'll give you the effectful one.
So it's kind of interesting to see that we have both fold L and fold LS.
Yeah.
Right, one of the criticism of having monads in the first place is that you have now all those same things for monadic code and non-monadic code. And so the question is, can you escape S if I have a worker function that actually does not perform any effects? Could I still somehow apply fold LS and
Yes.
then get out S?
I used to be really worried about that. So I also have a fold LM because this system deals with state-like effects like read, write, allocate, console, sleep state like things. Whereas monads can also be used for parsers and exceptions, and it's a more general notion. So
I mean, one question would be whether you need the first one at all, right?
Right, that's my question.
Yeah, I mean, or to say it in a different way, like, why not have, I mean, you probably thought about this, why not just have all things always return SEB, where E can just be the empty set, right?
So that the answer to that is that in the first version, there's no way to observe the order evaluation. So that explanation makes more sense with the map. So suppose you have the pure version of map and then this effectful version of map. With the pure version of map, there's no way to observe the order in which the elements are handled. Like, does map take the first element and apply the worker to it, and then the second element and apply the worker to it, all the way to the end? Or does it start from the back and go from the back to the front? Or does it chop up the list into two pieces and then run them both on separate cores of your machine? With a pure version of map, there's no way to observe what the evaluation order is. But then with the effectful version of map, there is a way to observe the evaluation order, because you can write a worker function which performs an effect and then, like prints to the screen. I have processed the first element, I have processed the second element. So moving between the pure version of map and the effectful version of map, even though the body of the function might happen to be the same, because it just so happens that the pure version deals with the list elements from left to right, and the effectful one also does. They really mean different things.
But doesn't that depend on the effect? For example, if the effect is read, then you could still do it in arbitrary order and it would work out all fine.
That's right. That's right.
So I guess to get good performance, you would kind of need to specialize the body to each kind of effect.
You could specialize it, potentially.
But that might well make sense that you say I specialize every free effect to just pure once, and thereby save half the code.
Yeah.
Because it seems like, I mean, if you have this strong agreement between the pure and impure version.
Yeah, yeah. That's. I have ideas about that, but I haven't gone anywhere in that direction. Yeah.
This is a funny suggestion, but what if you wrote two type signatures for the same code and then just accepted that you've got two different functions
You
out
can
of it?
treat it as this or treat it as
Yeah.
that. That's a good point.
And I guess
But then if you allow E to be nothing, right, then this is essentially kind of comes with this, right?
Pardon?
Like if you allow E to be like no effect, then can escape S somehow, then it can essentially try to do this, right?
That's
If
right.
you specialize the fact that there is no effect, then you essentially get the pure thing.
Yeah, so the usability of this, I think this is better in some sense. Well, it can do some more things than the existing Haskell system, which we saw with pattern alternatives. But I don't think it's a complete solution, particularly because it doesn't handle, like we have these built-in state effects, but we also sometimes want to use monadic effects, which are different things. And there's some deep theoretical work about how to build a bridge between those two worlds, the built-in notion of effects and the monadic notion of effects. There's work done by Andrei Flinsky. He's written papers called Representing Layered Monads, where you have operations which can take a computation which is typed as having a built-in effect and then reify it into the monadic encoding, which does the state passing and then also back the other way. This is called, paper is called Representing Layered Monads. And in that paper he also makes the observation that all effects, and by all effects I include exceptions and parsers and maybes and everything like that, can be implemented by a combination of the primitive state effects as well as continuations. You need to have some notion of global state, which gives you sharing, and then continuations allows you to adjust control flow in interesting ways. So if you have state and continuations, you can implement all the interesting monadic effects as well. So, but my implementation only does state, I don't have continuations. So it's, maybe I could extend it, but at the moment I'm focusing on state. So that goes further in that direction to reduce the number of versions of this. I think you need to implement primitive continuations and then go the Flinsky way, but I don't think anyone has done that yet. Yes?
Isn't that what the transformers F library from Holyjaws does? So taking the effects, transform into a monad transform.
So all of the Haskell libraries are embeddings of notions of effects into a pure language. It's essentially church encoding the control flow that these effects give you. You know about church encoding, like if your language doesn't have primitive natural numbers, you can just write lambda abstractions which do the same thing. Or if you don't have primitive if then else, you can code all those features up with just straight lambda abstractions. These libraries in Haskell, like transformers and MTL, are church encodings of the control flow which an effect system would give you.
So I mean, the transformers F.
Transformers
so
F.
One of those effects libraries, like extensible effects and.
In Haskell?
Yeah.
Yeah, they're still encodings because the Haskell core language doesn't have a primitive notion of effect. So they're all encodings.
Isn't there a scheme version of the Flinsky paper?
Pardon?
Isn't there a scheme implementation of the Flinsky paper?
I don't know. Maybe.
So in your language, you can't define your own effects. You're restricted to the ones that are.
No, I can define new world effects like console or file system effects or network effects.
But not like non-determinism.
That's right, because
Because you're missing the.
that's really non-determinism is a much deeper change because it affects the semantics of the core language. So these really do have to be built-in notions into the system.
So you need code CC in your core language.
Yeah, that would be nice, but I don't have it. Okay. Any other questions?
When you define your own world effects, can you tell the compiler how they can be reordered?
No, that would be nice to have. I think there's a language called Habit, which I think might do some of that. Habit was intended as a Haskell dialect for writing real-time systems. I think that was done by Portland State University, like Tim Chevalier and people like that. But I think that project died out a few years ago. Other questions? Okay.
Oh, we're already at the end.
Well, I can keep talking, but I have some more stuff I can show you.
I think I at least was just waiting for the next stuff to come up.
But are you waiting for the next one?
I was just waiting to the end to ask this question because I didn't know if you were doing that.
No, I have a bit more to show.
I was wondering if you could go back to the typing rule slide where you, because I got lost there.
Yeah, which one? This one? The bidirectional one? Or?
Yeah, go forward. That there, yeah. I guess what confused me, you might just have to go back to the beginning and just explain it again, but I guess what confused me was that you had type tau1, which I would regard to be like a pure type, and then you had the effect type S sigma tau1. I just wanted to know, you kind of related that to subtyping in the previous slide.
Yeah.
But I was wondering if you could just go through that relationship again.
Yeah, okay, so remember if you take the Barbara Liskov approach to subtyping, so Barbara Liskov was a computer scientist which defined what subtyping means. She said a subtype is, you have a supertype and a subtype, then you can do everything with the subtype that you can with the supertype. Is that the right thing? It's a substitutivity property. It's like if what I want is a fruit and I have an apple, then an apple is a fruit. Everything I can do with a fruit, I can do with an apple because it is a fruit. Okay, so that's the notion of subtyping. It's called a Liskov substitution principle because I can substitute apples for fruits because apples are fruits. Now this is slightly different. It's more of a sneaky hack. So I've hijacked the rule I had before, which has this subtyping relationship into it to do an implicit coercion. I say that what I want M to be is a value of type tau1. I can infer that the type of M is a suspended computation that if I ran it would give me something of type tau1 and also have these effects. So in the type system I say that's okay because I could change this M to run M and then the result of that whole expression would have type tau1.
Yeah. So you don't actually have run and box in your typing rules?
No, I don't have in the typing rules.
Yeah.
So if you're going to formalize this, so that's when you insert implicit coercions like that, it's called elaboration. So you could write down elaboration rules, which are like typing rules, but they show you the expression that you would have after type checking, after you've inserted all the implicit coercions.
Right. Yeah.
So GHC also does the elaboration. During type checking, it inserts dictionaries to implement type classes as part of its elaboration.
That's a good example.
Okay.
Yeah.
It also inserts type abstractions and type applications to produce a system F-like core language. So you start with a source code and then you convert to another language during type checking. That's else So I've only shown the source part, not the elaborated part, which would contain the run.
Right.
Also coercions.
Pardon?
It also inserts coercions now.
Yeah, GHC also inserts coercions to handle type families and GHCs and things like that.
I have a quick question about this rule again. So here, if you just write run, it's because it's implicit. in the conclusion of your rule. You write just n. You don't write run n.
Yeah. Okay. So
Because
this is a type checking rule. So this rule is used to check whether a source program is valid.
yeah.
So
in this case, so you said it's subtyping, so it's similar to subtyping.
yeah.
And the property we want with subtyping is that no matter how we infer where we put the coercions, we still have the same program. And for me, it looks like in your system, this coercion has actually an effect.
Yeah.
And depending on where we put them, we don't have the same semantic. And a simple program like, if we have a polymorphic functions that chooses, which would be a forward alpha, I take a bool, I take 2 alpha and I return an alpha, which is kind of verification of if. If we have this and we apply two elements which are S of something, I mean to closure, we can either instantiate it with the closure, in which case we only evaluate one of the two, or we evaluate both elements and we instantiate with the value of it. So for me it looks like this breaks one of the important points of subtyping, which is that no matter how we infer the coercions, we still have the same semantic interpretation of our program.
Yeah, so that's why you need to supply type signatures in some places to select which version you want.
Okay.
Yes.
Because actually we did not see the rule you have for polymorphism. I don't know how they are written with bidirectional programming, say bidirectional inference. Does the instantiation of a polymorphic term, does it synthesize or does it takes a type as a input?
So it depends on what framework you're using for bidirectional type inference.
Okay.
So the one I'm using is based on a recent paper by Neil Kalantan, Krishnaswamy, and Joshua Dungfield. They were at, with Bob Harper at that place in Pittsburgh, Chum. Oh, I killed my thing. Hopefully it'll come back. At CMU. So they released a paper about 2013 called Complete and Easy Bidirectional Type Inference for Higher Ranked Types. And that was at ICFP, and the contribution of the paper was a bidirectional type system which did higher ranked type inference. And in that system, instantiation of polymorphic types was handled by the subtyping judgment.
Okay.
So, for example, if what I want is a function from int to int, but I infer that m is a function for all a to a, that's okay because I can instantiate that to get a function from int to int. So that's also done as part of this elaboration.
Okay.
Makes sense?
And okay. And is it enough, or do we still need another rule?
Pardon?
Is it enough to have just instantiation as this subtyping judgment rule, or do we need another rule also in case?
So in that paper, there's 3 classes of judgments. There's these synthesis and checking rules for the bidirectional type inference. There's a set of judgments which deal with subtyping, and there's another set of judgments which deal with instantiation. So there's 3.
Okay.
But then the subtyping judgments call under the instantiation ones, and it's set up in a way which makes higher rank polymorphism work.
Okay.
So that's you'd have to read the paper to get more information about that. But I've implemented that whole system, so the type checker I have also does high ranked polymorphism.
Okay.
I think that in your system, then you said you would have to put an explicit documentation to choose between the 2 versions described. But does it force you to do so, or sometimes does it choose for you and doesn't tell you?
Sometimes it does the wrong thing. So you put your hand up a few times. Did you have a question? I'll go back to that one. I can show some code.
Not on the type system, but rather on the uses of the language.
Yes.
Do you have ways to deal with memory?
Ways to deal with memory.
Yeah.
Yep, so now
you know, that not the garbage collector takes care with which regions you reuse.
yeah. So I'll push your question on the stack and then go back to the other one, and I'll show you another. So I thought your question might be shorter, but I'll get to that. Yeah. So the other one was that. Sorry about that. But where does this break down? Show me a case where this all goes to bits and it doesn't give you what you wanted to have. So one of those things happens in the text-based library, where here. So this, I'm just taking two text strings and I'm comparing them for equality. So text is just a heap allocated object full of characters, and then on the outside these EQ text is pure. It just takes two text strings and then returns a boolean to say whether or not they're equal. But then internally it's reading the vector which holds the text characters. So this function go is a tail recursive loop which reads characters and then checks them for equality. So you can see the type of this function is sReadR bool, where R is the name of the region which the text data is stored in. And it so happens that I must provide this type signature for this to work. So I can't take that out and then successfully type check this code in my current implementation. The reason for that is that my type inferencer is too local. So if you look at each of these alternatives in turn, the first one is pure. So once you've taken the look at the first alternative, you expect that the result of this is just a Boolean value. But then when you go to the next one, you find out that this alternative is an effectful computation which will do a read and then return a Boolean. So it'll say this alternative is pure, this alternative is effectful, bool does not match type S read bool, but it's too late to insert the coercion, so I get a type mismatch. Okay? But if I put the type signature in, then while it's checking this alternative, it knows that the result type is supposed to be effectful, so it'll insert a box here before it goes to the next alternative. So in that sense, my checker is too local. I should really do some local constraint solving and then fix that up. So does that answer that question?
That's actually a super interesting piece of code, right? Because this is actually answering a question that I wanted to ask about something like an ST monad, where you basically guarantee that something doesn't escape, and that's what you.
So now I'll go back to your question and answer.
Yeah, okay.
Both at the same time. So here's the next bit of this. So I have regions and capabilities. No, hang on. How do I go back to
Play?
Pardon?
Is the play button there?
So in this system, I've skipped over what this R means. The R is a region variable. So in this language, we have the heap, which is the place where all the objects live. But instead of just being a homogeneous heap where you just throw all the things in the heap can be divided into regions, individual regions, and you say this object is allocated into this specific part of the heap, and this region is different from this other region. So these regions, this idea of region is also a baked-in notion into the language. And the way you introduce a new region in the heap is with this private construct. You say, I want a private region called R, which is a little place in the heap, which you can allocate into. And then this information over here is capability information. I say, in my new little region of the heap, I'm going to allow read access from that region, as well as allocation of new objects into that region.
But R cannot escape now.
But it cannot escape, that's right. So
That's enforced, right?
So yeah, so here we go. So we got, in this example, I'm going to create a reference called R1. I'm going to allocate a reference into this region, initially holding the value 5, and then I'm going to read the reference. Now, the body of this construct has type nat, so I can return a pure value from that construct, but I can't return an object in region R because objects in that region are supposed to be local to the private construct. So this is statically checked. So in the traditional region systems, these regions are allocated in a stack-like manner, which means that when you start this construct, you allocate a new region, or initialize a new region. You can allocate objects into it, and when you leave the construct, the region is automatically deleted, and everything that was in it. So there was a language called MLKit with regions, which first introduced this idea. So in my implementation, I have region types, which I use to attach capabilities to, like read and alloc, but I haven't implemented the automatic deallocation. Okay, I haven't implemented that in the runtime system.
You're using here do notation? Couldn't I use just a let?
Do in this system, do is just a sugar version of let, but the same thing. Okay, so we talked about these region variables. So here's the type of these primitives. So alloc, I have an A thing, and I can allocate a new reference to an A thing, and the reference is allocated inside the region which I specified. And to allocate the reference, I must perform an allocation effect. Reading a reference performs a read effect, and writing a reference performs a write effect. So here's an interesting mechanism. I also have an extension form. So what you can do is that if you have an existing region, you can say, I'll explain the concept first and then I'll go to the code. You can have an existing region which is immutable. You only allow allocation and read from it. An existing region which is immutable. I'm going to create an extension region which I allow read, allocate and write into it. So I allow write effects into the extension. I destructively initialize objects in the extension, and then when I'm done, that new extension joins my existing region, now with its new initialized objects. Okay? This is very useful for initializing immutable arrays. Often the case in Haskell programming, you want to allocate a new empty array, destructively write all the objects into it, and then say, okay, now I've initialized this array. From this point forward, that's immutable. Okay, so in Haskell, they use hacks like unsafe freeze array or unsafe freeze vector. If you've used the data vector library, there's mutable versions and immutable versions, and you use these hacks to coerce between them. So in this system, I have safe freeze array. So here we go. Here in my private construct, I create a new region R, which is immutable because I only allow read and alloc effects onto that region. Now in this statement, I'm going to allocate some more objects into this region. So I'm calling this function. This syntax says I'm going to take my existing region R1 and extend it with a new piece, which I've locally called R2. And then onto the new piece, I allow write effects as well as allocate effects. Okay? So in the new piece, region R2, I can allocate a reference to the value 5 and then write into that reference onto R2. And then I return this reference in R2, but then when I leave the scope of this extend construct, region R2 is joined into region R1, and I lose these local capabilities. So once I've returned from this construct, I can only do read and allocate. So I'll step through that. Yep.
Quick question: Could I have extended in the scope with R such that I can both read from R1 and write to R2 at the same time?
Yes.
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 That's pretty cool, because then you basically, the compiler has freedom to say reorder the writes with reads, right? Because they're guaranteed not to alias.
That's right. That's right. So here we go. So you look at here's the types. So I say, in the body of this extend form, what's the type of this code? Well, the type, so this ref2 is a reference in region R2 to a NAT, and the effect of this is to allocate into that region and also write. So this line does allocate, and this line does a write into region R2. And you can see on the right-hand side here, this is the current situation. I have the original R1 and my extended part R2. And I'm allowed to write into this, but not into that. So I do my writes. But then, what's the type of the overall extend? Once I leave the scope of this, the body of this ends up having type ref R1, because look over there, I've forgotten about the local part R2, and now everything's just R1. And then, because I allocated into R2, that was like allocating into R1, because I can see I've got more objects in there now. But there was no way I could have observed the write effects. There was no, because I allocated objects, and I only wrote to the new objects, not the old ones. So the caller could not see those writes. So as far as the context is concerned, this piece of code only performed an allocation. So yeah, in this system, this extend primitive is safe freeze array, not unsafe freeze array. So I've got safe perform IO and safe freeze array. And it's simple, that's it. Thank you. I'll stop there. I think we're out of time. Unless there's any final questions. Yeah.
How does that compare to COCA, the non-legend language, COCA?
Yeah, we've both been developing these systems sort of in parallel. So COCA, it's been through a few versions. My understanding of the current state of COCA is that it's based on polymonads. So what that means is, you know how in Haskell's bind, the type of bind is like MA to A to MB to MB, right? And the reason the Haskell's bind is annoying is that all the monad types have to be the same. So I have MA to A to MB to MB, so they all have to be the same. So which means monads don't compose. With a polymonadic system, you allow those monadic types to be different. And then there's meta rules to say what combinations are valid. I think the current state of COCA is based on that. So it's based on return and bind, and it does some extra inference to work out what monadic effects everything is. So whereas this system is based essentially on a modal logic. So this S thing is a modal type constructor, and run and box are based on primitives from modal logic. So and then we have this private and extend, which comes from the traditional literature on region type systems. So another system in this field is Meso by Francois Potier, which is based on linear capabilities and type state, which is another direction again. So they're all sort of in the same space, but they approach the problem in different ways.
But both you and COCA, you don't have annotated arrows like you wrote at the beginning. You have this indexed return type.
That's right, because that's the best way to do it.
So from a user point of view, is there a difference between using DDC?
Yeah, all these things are still being developed. Like, there's from the user point of view, there's things that are problems in my current system, like the one I showed you where it does the alternatives in a particular order, but that can be fixed with a little bit smarter type inference. I can't express the fundamental limitation with any of these systems yet. I think they're a bit too new. Yep.
Closures are also allocated in regions? Or do they have a special region that's closed?
So as a design decision, I decided that there will be a top level region which just exists forever, and closures are allocated into the top level region. So in the very first version of this I wrote for my PhD, the closures are also allocated into their own regions, and every function arrow has an effect annotation as well as a region annotation to say what region that closure is annotated into. But I think in an engineering sense that's unusable because you end up with too many variables to worry about. So I decided not to do that. I think another reason for that is that if you read the literature on region typing, they say that if you read the literature on region-based memory management, where you have stack allocation and deallocation of regions, they say that region-based memory management by itself is insufficient for general-purpose programming because the lifetime of the objects must follow the syntactic structure of the code. But that's not always the case. Say you're writing a web server, and someone connects to your web server, you have to allocate some objects, and then when they disconnect, you have to deallocate them. The time that you have to keep these objects live is not statically known, and hence you can't statically do the memory management based on type information. So in a practical sense, you have to combine region-based memory management with a garbage collection system. So I figured that if I have to have garbage collection anyway, I might just put all my closures in the garbage collected heap and not worry about them.
All right, cool. Thank you very much, Ben.